Looks like we got most everybody back from the break, so that's exciting. So I didn't scare you all away. So next up, we have part 2. I know we're a little bit behind time, but I think we'll probably make up time. This part, if we don't get to it, it's okay. I have some code on GitHub, so you can take a look at that. I won't be able to explain it all today anyway. So the main things we're going to cover now is the ML with Medicare data. We're going to use a Jupyter notebook that I just launched during the break with a nice big hefty machine on it. We're going to do a bit of a toy machine learning problem, and then we're going to do RStudio stuff with a shiny dashboard. This Jupyter section right now, if you're already familiar with Jupyter and pandas and scikit-learn, you might get a little bit bored, but maybe it's a new problem for you. So I'll introduce the data, and we'll do pretty much an end-to-end data to ML model kind of workflow. Explore a little bit, train a model. And then what I'm going to do is launch up a sort of like a grid search style thing that I'll be running, saving data to S3. And then as we build the R code, we'll actually be able to get the files live from there. So here. And so there's this paper from my research group called Predicting Medical Provider Specialties to Detect Anomalous Insurance Claims. I'm going to use similar data, and we're going to do a similar machine learning problem from this paper. It's not the same code, and it's not the same process, and not exactly the same data, because then you could just steal our paper. But at least this gives you context if you really want to read up a little bit more about this problem. Rich Bowder, Matthew Herland are a couple of my colleagues who have both graduated with their PhDs all around Medicare fraud detection. I was involved in this paper, but then later on my research went in a different direction. So I do have a GitHub repo. If anybody wants to look at that link, it's the same name, RIKTURR, the same place I am all over the internet. If you click on this repo, you'll see a little bit of code similar to what we've been doing now. I'm going to update these examples because this is about a year old now, but from what we do today, I'll update the GitHub so you can grab it. So it'll be all in the communication. The conference will send out an email or put it on the website with the GitHub, the slides, the video, everything. So first thing we're going to do is a bit of data processing. Then we're going to do a random forest model with scikit-learn. And then I'll show you a previous notebook that I saved off that does Keras. I'm not going to do the Keras deep learning stuff live. I just want to show you that it's possible. All right. So if we go back to my console, while we were in the break, I restarted one of my other EC2 instances. This is a C5 9x large. This has a bunch of CPUs and a bunch of RAM. I don't know. Let's see. So this is my screen. I'm going to disconnect from my screen. I'm going to do HTOP. So 70 gigs of RAM and 36 CPUs. And we're going to need all of that, as I'll show you. So I'll be bouncing back and forth between the screen to show you how we're using our resources. But I'll go ahead and I'm going to upload a little bit of a notebook. Again, these are all be on the GitHub, and we'll make sure that everybody has access to this code. So I'm going to start here, and I'm actually going to try to live code it, so we'll see how this goes. I have the answers somewhere else in case I fail. So this is just some code here. So if we want to dive in a little bit about the data, you can see what we're doing is we're getting data from CMS, which is the Center of Medicare and Medicaid Services, which is the U.S. basically healthcare provider for individuals over 65 or specific other individuals with specific conditions, but generally it's 65 and older. And this particular data set, I have essentially the data dictionary here. I'm not going to be able to explain fully what this data is, but if you're familiar with any healthcare system, what this data represents is you have data about each doctor. There's an identifying number for each doctor. And we get every single procedure that they performed in a given calendar year. So we'll get the doctor, we get the procedure, which is the specific code that's used for billing, and then we get the number of times they did that procedure. We get the average amount of money they received for that procedure. So it's a little bit aggregated, so it's not going to be identifiable to any patients, but it is a public use file that the government releases. Generally, it's a couple years behind. So now we're at the end of 2019. You can probably get 2017 or 2016 data right now. They started doing it around 2012, so you can get a few years of data, and the doctor identifiers remain the same across. So if you want to, you can just Google like Medicare public use files, and you can probably find this, but this specific public use file is all about the procedures that doctors perform. So I'm just going to go into kind of what data that we end up using. You can read all about this, but what I care about is the contents. So you can read, there's some maybe 30 features in this particular file you get. It's a big giant, I think it's a tab delimited text file. It's a big giant text file, and it's maybe like 3 gigs, I think, the whole thing. And if you put every year together, you know, now you're talking 10 gigs, 20 gigs. But the main identifier is the NPI, which is a National Provider Identifier. Every doctor in the US has one of these. So it's a unique identifier for that doctor. It's just like a 10-character integer. You have some stuff about the providers. We're not going to use that right now. What we're going to care about is provider type. We're going to look at that. So that basically means what kind of specialty are they? Are they a dermatologist? Are they internal medicine? Are they cardiologist? And we'll look at that data a little bit. Place of service is where they perform the procedure. So was it an office, or was it a hospital or a facility? And then the important stuff here is this. It's pronounced, because I work in healthcare, I know it's pronounced HCPCS, so HCPCS code. That's a 5-digit code that represents a medical procedure. And that's how doctors bill insurance companies. So they say, okay, I did a 99213, which is a office consultation, and they'll bill that to the insurance, and then the insurance knows what they're paying back for that thing. So in this case, our insurance company here is Medicare. So this is all of Medicare for the whole country. And this data set, I think we're using the 2015 data. So we'll see that code. So that has the code, and then it has a description. And then the last thing that we're going to look at, so basically, essentially how this data is there's doctor. The doctor can perform maybe 30 unique procedures over the year. And then the data for those 30 procedures is these kind of numeric values. So there's line service count, which basically just means how many times did they bill that procedure. So, you know, it could be 30 if it's infrequent. It could be hundreds or thousands if that doctor is doing the same procedure all the time. And then there's other metrics around like the number of people, the amount that Medicare paid, so on and so forth. There's a whole bunch of other data, but what we're going to focus on now is the provider type, the HCPCS code, which is the identifier for the procedure, and then the line service count, which means the number of times they actually performed that HCPCS code. So you're going to get a little bit of dupes in the data, and I'll show you. So that's the background.
Just out of curiosity, is there any outcome data stored in these things?
Outcome?
Whether the patient survived or how well they did? Or?
Probably not, because Medicare is just the payer. So you're not going to get necessarily the outcomes unless they do specific studies, you know, to work with those populations. But there's a whole other ton of data. There's like data about the drugs, right? Part D with Medicare, which is the drug part. Part B is this, which is the procedures. But I don't know necessarily that there's outcomes. You could probably link to like death registries for some stuff, like if death is one of your outcomes, but not like very specific medical outcomes. Okay, so that's our data. One thing that we just have to do here, and can everybody see that in the back? Should I zoom in more? We're good? Okay. Right now, this AMI comes with pandas 0.24, and because I haven't done my research in a few months now, I was using an older pandas version, the 0.21, and it caused some issues, and I found this out like 2 days ago, so I didn't have time to fix it. So for now, we're just going to have to do a pip install. So if you're not familiar with Jupyter, if you put this exclamation point at the beginning, it's going to execute a system command, so essentially a bash command. So I could type this pip install pandas from my terminal, but it's nice just to have it in the notebook. If there's no exclamation point, it's going to execute regular Python code. So I'm going to run that. Oh, I already ran this. So because I ran this 2 days ago, and I stopped the machine, it kept my EBS volume, so that means the same thing was available. But if you get this notebook and then download it, you're going to have to do this if you use the same AMI as me. If you use a different AMI, you know, your mileage may vary. So we'll start here and import a few packages, and then the rest of the code I'm going to kind of try to do it live. I'm a pretty fast typer, so we should be good. So we'll need pandas, NumPy, matplotlib just for some plotting, and SciPy because of the data processing that we're going to be doing, we're going to have to create a sparse matrix, and I'll show you. So the matplot inlib magic, which is the percent, means it's a magic command, just means show me the graphs inside. So I have data on my bucket. So if I go back to my Amazon, I'll go to my S3. I have a public bucket that I created, and I have some files here. So what I did is I downloaded the data from Medicare. You can get it from them. It comes in a zip file, and you can unzip it, no problem. But I put it here on S3 just so it's easy for us to grab. If you end up doing this at home, like, don't download it to your laptops a bunch of times, because then it's going to charge my Amazon account. So keep it inside EC2 if you're going to do anything, please. So I think what we're downloading is this part B file. So it's about a 2 gig text file. So 2 gig doesn't sound too scary, but when you try to do a lot of processing on it, you're going to see it's going to take a lot of stuff. So my bucket name here is RIKTURR. So I'm going to build my URL accordingly. So I'm going to go over the command line of Amazon a little bit later, but for now, I'm just going to do a couple quick commands. This is terminal, so I'm actually running this in bash. If I say AWS S3, now there's a whole bunch of commands available to me, just like any other file system. So if you're familiar with the Unix file system, there's ls, rm, cp, all that kind of stuff. So I'm going to do ls and say s3 : / all S3 URLs are going to start with the s3 : / and then here's my bucket name. So if I run this command, it's going to show me the same things that we just saw here, same files. Right? So 2015 part B.text, all that stuff. So that's this command. Okay, so what I want, though, is that's just showing me what's available on S3, and that's available all the time, whether or not my machine is on or whether it's off. What I want to do is I want to download it from S3 onto my EC2 instance. So to do that, it's AWS S3 CP. So I can give it my URL, and I just want this one file. So I know it's called 2015 part B. So unfortunately with S3, you don't get auto-completion like you would in a normal Unix file system, because these files don't exist anywhere. So now I'm saying copy this file into wherever I want. So the copy actually works if you want to copy from S3 to S3, or S3 to your local, or your local to S3. That CP works any direction. So, but in this case, I want to download it to my local place. So I'm just going to put dot, which if you're not familiar with Unix, just means my current directory. So I'll run that. See, it's copying 2 gigs, and it's really quick because it's going from Amazon to Amazon. They optimize that kind of stuff. So now, if I do just a regular ls, we can see now I have my 2015 part B.text right there. Yep.
So just to clarify that last step, you just copied from your S3 bucket into the hard drive.
Correct. Yes. So if I were to stop this instance, that data now also lives on this hard drive. If I restart the instance, it would come along with it.
And if you terminated it, it would go away.
It would go away, correctly. Correct. Okay, so now I have it on my computer. There are some actual ways, and we're going to get into it later, where you can use a Python API to directly grab from S3, so you don't have to stage it on your hard drive. You can actually just load it into memory straight from S3. There's a different package for that. I'll show you that in a second. But for now, I have pandas, right? Okay, I have pandas. So I'm just going to come up with a very good data frame name, and I'll read this CSV. So actually, here, if we want to see it, we can do head. Actually, this should autocomplete, I think. Yeah. So that's what our file looks like. It's a big tab delimited file. So, and I know it's tab delimited. It's very clean, so I've already looked at this before. So this isn't completely from scratch. So I'm just going to go ahead and grab that, pandas. And I know the separator is a tab, so we're good to go there. And that'll take a second, right? Because it's loading a 2 gig file into memory, right? So we can see here now that we got a processor spinning, doing some stuff, and my RAM is starting to increase. And it should stop right around 2 gigs, right? And of course, and materializing anything inside of RAM is going to be bigger than what it is in the file system usually, especially if your file is already compressed. I mean, this is a regular text file, so it's not going to be that much more, but if you have it like gzipped or something, of course, it's going to be a lot smaller. So, okay, so warning, we'll ignore that. So exploratory analysis, I just want to do some nice data science practices and just look at it a little bit. So this is pandas code. Let's look at the file a little bit. So looks like our first row got a little messed up. I think the contents of the text file has some garbage at the top. But now we have our data. So this is MPI. That's the unique provider code that I mentioned. And you can see how this is repeated for the same doctor, right? This is this particular doctor. And this particular doctor did this 99217, which means hospital care discharged. They did that 23 times. So those are the columns we care about: the MPI, the code, and then the line service count. Okay, and we'll look at the data a little bit more, but first we want to get a feel of the shape of this. So okay, how big is this data set, right? So we'll do shape. You can see there. So we have 9.4 million rows and 26 columns in this data set. Materialized in memory takes around 4 gigs right now before we do anything with it. So we're gonna fill that right up, don't worry. So just to check, we kind of previewed a bit of the data there, but let's make sure we can see all of our columns and all of our data types. Here we go. So usually, if you not use pandas, usually it reads any strings as an object type. But MPI is a number. We're going to use MPI. We're going to use this provider type, which is also a string. We're going to use the HICPIX code, and we're going to do the line service count, which is a float. So our data is nice and clean to a degree. So let's look at those fields that I care about. So again, like I have a little bit of domain knowledge on this particular data set, so I know that this is really what we care about. So the NPI is our unique identifier for each doctor. The provider type is what we're going to actually do for prediction. That's going to be our class label for this machine learning scenario. We need to care about place of service because you'll see in a second why. HICPIX code, I'll go ahead and grab the description too, and line service count. And let's make that nice to see on the screen. So if we look at all these fields, now we can see it all together. So see how this MPI is repeated a bunch of times because the doctor basically does a bunch of procedures. So essentially, you can think about one row in this data set is NPI, place of service, and then HICPIX code. So technically, this 99217 can show up multiple times if this place of service was a different place of service. That just means one doctor can work in a hospital on Mondays and then they can work in their private practice on Tuesdays. They get paid differently based on those different facilities, but it's the same code. So we have to deal with that, and I'll show you that in a second. But so really what we're doing here is we're going to take these codes and we're going to see if we can predict the provider type. So the provider type becomes our class. So basically it's saying, and this is kind of intuitive, that the behavior of the doctor, the types of things that they do, the types of procedures that they perform on patients should have some signal and describe what specialty that they perform under. And so that's what we're doing. And then the idea with this particular work and this particular paper is sort of a fraud detection type thing. So let's say if 99 dermatologists all do the same procedures, but then this one dermatologist is doing some weird stuff with the eyes or doing other things that a dermatologist normally isn't doing, we could say that's potentially, at least it's an abnormal case, and it's worth investigating more for potential fraud or for abuse. So that's the idea. This, of course, is not going to get you to replicate the particular study that we did, but it's the same general problem. So because of the fact that we have multiple rows, and so basically what we want to do is predict each doctor as an instance. So we need this NPI to only show up once. So we're going to take this, we're essentially going to pivot the HICPIX codes, and we're going to turn these codes now into columns. And then the provider type is going to be our class. There are a bunch of HICPIX codes, and I'll show you that actually in a second. Actually, I'll show you that right now. So if we grab df HICPIX code.n unique. So there's 6,000 different codes. That means you're going to get 6,000 columns once we do this pivot. So that's going to make like a pretty big data set. It's also going to make a very sparse data set. Because let's see if we can do, I'm doing this on the fly, I didn't plan this. So let's see if we can group by the MPI, and we'll take the HCPCS code dot unique. And so now that should give us the number of unique codes that each doctor sees. So we can see that these are all in the less than 30, right? So most doctors do a small subset of all the possible procedures that can be done. So if you think about when we do this pivot, it's going to be a bunch of zeros. And that's why we're going to do a sparse matrix.
So the group by command in pandas is basically grouping all the individual doctors, their IDs. And then why do you need the HCPS? Because it seems like it could group that, and then you had two other columns that you were using.
Oh, so this point, so like in SQL, this would be similar to, so basically I'm saying group by the MPIs and count the number of unique HCPCS codes that belong to each group. So this group, like this doctor, 1300126, they do 11 codes right here. So then it would count it for each doctor.
Why needed the secondary brackets there? It seems like you could have just done like group by,
Oh,
group
yeah.
by, and then the number of unique ones would have got you back to the 6,000. But
Yeah, you could. So actually, it's a pandas thing. You didn't have to do that. That's if I wanted to count the actual unique codes, but technically I could have done like ag. I don't remember specifically, but pandas does this weird thing is if you don't put a column in the brackets here, it's going to apply your aggregate operation to every single column in the data set, which would make it like, so if I just did n unique now, I think it would apply it to every single column, and it's going to take a long time. So now it's going to count the n unique for first name, last name, description, all the other random things, and that's going to take a long time. So I'll kill that. But now what this code says is only count the unique HCPCS codes, because that's what we care about.
Shortcut, because you just really cared about the number at the end.
I just cared about the unique of this particular column. That's why I got that. So if I do like, so now if I take this and I do that, now I can do an aggregate here, and I can say p.mean. Let me see this. Oh, actually, I think I can just do np.mean. Yep. So the average number of procedures that a doctor does across the whole data set is 9.5. So most people only do a very, very small number of procedures. Okay, so that's essentially our features, right, are these things. We still have to do the pivoting, but the next part we care about is the class label, right? So is the provider types. So we go back up here, it's this column, provider type. That's going to be our dependent variable. So what I want to do for now is just let me grab the, so I'm going to grab the provider type, and I just want to see how many, I want to see what we got. Like I don't know what's in there. So we'll do value counts, which says basically do a group by count the number of unique, count the number of values. So what we did here was the number of unique, but here I want to see the unique, actually it's the same thing. But so we see here the biggest group of doctors that we have is diagnostic radiology, followed by internal medicine, family practice. So that kind of makes sense, right? Those are the most you would want to see. So we're still in the millions here, millions for those, and then a bunch of others here. But I actually want to plot this, so let me save this in a variable, just so we can see the tail, because there's a whole bunch, right? So there's 91 unique provider types. And so with these numbers, it's hard to see the relationships between the biggest group versus the smallest group. So let me just go ahead and do this. I need to reset the index so I get a data frame. And then what's nice with pandas, it has some handy plotting, and you don't even have to deal with matplotlib because it's horrible. Par, and we'll do, so what this is going to do is it just takes this column and it's going to create a bar plot. Okay, So I don't have the labels on the bottom just because I didn't do that. But if we look, the first 10 providers or so, or even the first 2, 3, 5 is really our biggest group, right? There's a big long tail of all kinds of different other providers that we've got. So just because this is a toy example and I'm not really trying to explain fully this problem, but at least it's good just to see. We're just going to take the top 10. So we're going to filter our data. We'll take the top 10 group and see if we can discriminate between these 10 classes. Because if we were to do the machine learning problem on all of them, now we have 91 classes that we're predicting, or 91 labels, or different unique class labels that we could predict. So that's just going to make the confusion matrix like way too big. So I'll just take the 10 for now. So we're going to take the top 10 specialty types and actually let's save a sparse matrix. We're going to do that later. Okay, so we're just going to take the top 10. So if we say provider types, where provider types dot index is less than or equal to 10, this indexes these guys, and then we'll say top 10, and then we'll look at top 10. So these are our top 10 now. Radiology, internal medicine, family practice, and so on and so forth. So what we're going to do is just filter our data down to just these classes and then see if we can build a model that'll predict the class. So let's see. Yeah, just for my own sake, I named this something else on my notes. Otherwise, I'm going to get too confused. So same thing. Okay, so then now our top 10, we're going to take our original data frame now and just filter to anybody that's in this list. So this is saying, this bracket means filter this data frame, and then we're going to say based on this df.provider type column is in our top type, and we can see this column name happens to be index, so we can just say if it's in those things. And then it's the same data that we showed before, so I'm not going to show the whole data frame, but now we can see the shape of that. So same columns, right, because we just filtered the rows. Now we started with like 9.5 million rows. Now we have about 5.7. So it's still a lot of rows, but for this example, I wanted to limit our classes down. Let's check our usage. So we're still pretty good. We're chilling. 5 gigs of RAM. None of the CPUs are happening. So technically, this notebook you could run on a much smaller instance type, and you'd be paying a lot less. And then when you really wanted to do machine learning, you would launch the new one. But for simplicity, I just did the big one to start. Okay, so now we're gonna flip. We're gonna do the pivot. Right, we're gonna take this and we're gonna create the HCPCS codes as the columns. But to do that, remember there's this place of service thing. So technically, you could see this same code twice. So just for simplicity, what I'm going to do is I'm just going to sum the two numbers. So if I see 99217 twice for the same doctor, I'm just going to sum the service count. There's some considerations about if it's in an office or a hospital, but for now, just for this example, I'm going to do it. Because otherwise, if I try to pivot when there's dupes, it's gonna blow up because it can't do that because it can't create the same column twice because it's going to have the same name. So anyway. I'm going to do this. So I'm going to take my top 10. I'm going to group by essentially all my columns that I want, which is the NPI, the HCPCS code, and the provider type, right? So those things. Those are my other features, and then essentially, so I'm ignoring the place of service, but once I do the sum of the line service count, then that's going to essentially eliminate that for me. So what I'm saying here is group by MPI provider code, and then give me the sum of the line service count. So now in my new data frame, I'm going to have 4 columns: NPI, type, HCPCS, service count, sum. And then I'm going to reset index just because when pandas does a group by, it puts all the group by elements as your index, and I just want them as flat columns. So that's going to take a second. Oh, I messed something up. Oh, needs to be brackets because I have multiple columns. There. So that's going to take a second because it's going to group by those things and then do the sums. But now if I look at a little bit, now it's much cleaner data. I basically eliminated all the columns that I don't care about. So now I have MPIs, provider types, HCPCS code, line service count. And if I check the shape of that, now see I went down from this 5.7 million to 5.5 million. So there's only a small number of doctors that are doing the multiple codes in different places of service, but it would blow up your code when you try to do the pivot unless you do that. All right, cool. So next up is the one-hot encoding. So this is where we're really going to do our processing. So the one-hot encoding is where we're doing our pivot. It's not really one-hot encoding because essentially what we're doing is we're going to take this number, it's going to be the column, and then we're going to insert the line service count as the value. So it's not really one-hot encoding because one-hot is 0, 1. It's really more of like a count type encoding. It's really just a big pivot. So, but I still call it one-hot just because it's the same concept. This is pandas function called pivot table. I don't have the time to explain it now, but you can look it up later. So essentially what the pivot table is, we're going to say, I want my original columns, essentially is a group by, right, of NPI provider type. I want each row now to just be one row per doctor, whereas before it's one row per doctor per code. And then my columns now is going to be the HCPCS code. So that's saying it's going to say pivot on this. Take the values of the HCPCS code, convert those into the columns. And then it's going to say the values is the line service count. So it says take this number is now the value once it's pivoted. So we can see that. That's what's going to take the longest as far as processing, and that's going to start, that's going to start to eat up some RAM. Oh yeah, so I'm SSH'd onto my instance. If you type the command top, this is just a Unix command, it gives you the performance, but this one is like kind of messy. So I installed this other one called htop.
Right,
Yeah.
that, and then on your htop, I couldn't see what you were saying.
Oh yeah, so this 1 to 36 is all of our CPUs. So this particular machine has 36 CPUs, and it shows us the resources. And this memory is what I'm watching right now. So you see as this command is running, it's really increasing the memory because we are just, basically we're storing like a bajillion zeros right now because it's a sparse matrix. So now we're at 22 gigs. When we first loaded our data set, it was just 2 gigs. But if you try to run this on your laptop, chances are your laptop would have blown up by now.
It doesn't have anything on the memory in the green thing, which is what I was looking at.
Oh, yeah, it's right here. This shows you your so 70,000 megabytes, 70 gigs essentially.
Why doesn't it show it down here when you have your 6943 EC2 user?
Oh, that's one specific thread or one specific process. So this process right here that I have highlighted is what's using 20 gigs. Because if we scroll out, that's our Anaconda, Python, whatever. Yep. But I know I'm not running anything else, so that's why it's this. So if we look at the one hot now we see that our HCPCS has become our columns, and then our NPI provider type. I'm going to do a couple more things to clean up this data frame. So the pivot, so essentially this 00100 existed for some other doctor, but not this doctor. So it puts in an NA. I'm going to just tell pandas to fill it with zeros. What I'm going to also tell pandas is to reset this index. That way it becomes flat columns, just because that's how we want to deal with things. So we're going to say reset index to flatten out the columns, and then fill NA with 0. So all these NAs are going to become zeros. We'll run that again. It's going to take another second. But then it'll be a bit of a cleaner data set. So now this particular data set is ready for machine learning. Your provider type is now your class, and then you just got to remove your MPI because that shouldn't be a feature. That's just an identifying thing, and then you're ready to go. But what I want to show you is if you try to save this CSV, it's going to be huge. So what we'll do for this case is actually save a sparse matrix. It should be almost there. I'm going to type a couple commands right now. So we'll check the shape of it now.
Can you save a pandas file format onto your S3 and does it accept all those things?
Yep. So technically what you're doing is you would save a CSV to your machine, and then you can copy the CSV onto S3. Or you could save any other type of file that Pandas supports. You could save a pickle. Yep. You could save a pickle. You could save a feather. You could save HDF5. Anything that Pandas can do. Actually, and if you look at my GitHub, there's actually ways where you can use the Python API for S3, where you can directly write the object to S3. So you're essentially just writing. You would, rather than save the CSV to your computer and then copy the CSV to S3, you can save the CSV directly from Python. So essentially what you do is you create a string buffer for your CSV, and then there's the AWS API. You can save it directly. And I'm actually going to do that for the machine learning side. So we'll see that in a second. So you see, like, just to do this resetting index, filling, and everything, it's already eating up a lot of memory because it's just processing a bunch of zeros. And then it'll go back down eventually once it gets to it. So now we're sitting at 38 gigs of RAM because a 0 takes a lot more bytes to store than an NA, right? Because you actually have to store still whatever 32 bits, right? Because it's a float 32. But now we have our nice pretty data frame with a bunch of zeros in it. And now this is our actual unique doctors. So we actually have 500,000 doctors in this data set. And then now we have 4,000 columns. So we said 6,000 codes, but that's because we limited it to just the top 10 provider types. So now this is our real data frame. So this is 38 gigs in memory. I don't want to save a 40 gig CSV off. And it's because this is mostly zeros, we're going to use SciPy. We're going to save a sparse matrix, which is an optimized, compressed way of storing sparse matrices. Okay. So the first thing, though, is that sparse matrices only support numbers. So since our NPI and our provider types are strings, we're just going to save a CSV with those two columns. And then those essentially is our just unique identifier and then our class label. When we go to do machine learning now, we'll have the sparse matrix, which is essentially our X, our independent variables. And then our dependent variable is going to be this provider type thing. So first, let me create that lookup. And let's take a peek at it, make sure it looks good. So there we go. So MPI, provider type. And then I'm just going to save that to a CSV. I don't want the index. That's just this. I don't care about this. I just want MPI provider type. So we'll save that. Oh, wait. Oh, okay, great. So actually, this is because I already have an EBS volume, but if you didn't have this data folder, you would have to run this command just to make this directory. So now, if I do ls-lh, I think, data, we can see now I have my lookup file. Don't look at this. I had that from before. We're gonna create that right now. So, so let me show you first the size of the matrix, just to show you like why do I even care about saving a sparse matrix. We're gonna estimate what the size of this would actually be on disk. So we're gonna drop the NPI and provider type because that's technically not gonna be in our matrix, right? That's just how you drop the columns, the pandas. So then the matrix itself is going to be this dot values. And then if I print out the size of this matrix, this is once you do values, it's going to give you back a NumPy array. And if you do n bytes, just NumPy gives you that. So we'll do n bytes. We'll go to kilobytes, megabytes, gigabytes. That's going to take a second. So we need this matrix right here to be able to create the sparse matrix. But for now, this is just going to give me a NumPy array. So this is still a dense matrix with a bunch of zeros. So all of these numbers account for 16 gigs inside my memory right now. So I don't really want to save 16 gigs. So what I'm going to do is I'm going to use the SciPy package to show you to save the sparse matrix. So just so you see, again, just to illustrate the shape of this, we're talking 500,000 by 4,000. So if you multiply that together, that means we're storing, what is that? 100,000 million, 2 billion numbers. So that's a lot of numbers, and that's a lot of zeros to be saving. So what we're going to do now is use the Sparse, SciPy Sparse package. So if you go back up to my imports, I imported from SciPy, import Sparse. So we're going to turn this NumPy array into a sparse matrix. So sp.csc matrix. I don't have time to explain all the theory behind how the different sparse matrices work in SciPy, but this is one way to give you a matrix. So we'll say sparse equals this guy. So it converts our NumPy array into a sparse matrix, and we get sparse. That's going to take a bit of processing as well because it has to do all this stuff to figure out where all the zeros are, put things together. But while that's running, I'm going to have this other command now, which is how you save a sparse matrix. And that's where I'm going to. And for some reason, the SciPy saving stuff is like backwards. You have to give it the file path before you give it the object. Whereas if you saw the pandas, you kind of start with the data frame dot and then save. That always bothered me that they do it backwards like that. But now we have the sparse matrix with the same shape, but we see that we only have actually 5.5 million stored elements. So that means we have 5.5 million non-zero entries in our matrix, whereas before we actually have 2 billion total entries. So it's very, very sparse, and that makes it much smaller. So I'll show you that. So we're going to save it, and then we can see the size. What happened here? Uh-oh. I think I ran out of memory. That's not good. Okay, well, I needed a bigger instance. But anyway, here, let me just show you from here. All right, so that's only 18 megabytes. So 16 gigs of a, we saved that into a sparse matrix. Now it's only 18 megabytes. So let's say we were on a different instance type. Let's say I was on an instance which I guess needed more memory. But now, okay, I'm done for the day. I did my data processing. I have my nice clean data file. I'll come back tomorrow and do my machine learning. One option is you could just stop this instance. Your EBS volume would have your data. But the best practice is to go ahead and just put this file on S3 because now you can use it from anywhere after that. So the way you would do this, let me get rid of this. The way you would do it now is I would use my bash command as well. So AWS S3 CP. Then I would copy this file here, and then I would put it to wherever I wanted to go.
Can you also save your Jupyter notebook there?
Yeah.
Does your Jupyter notebook disappear, like if you're doing it
Yeah.
on this instance and then?
Yeah, if you terminate the instance, the Jupyter notebook would disappear. Normally what I do, because I keep them in Git, I go into File, download the IPython notebook, and then I store that on Git just from my laptop. But you could copy the Jupyter notebook to S3 if you wanted to.
I guess it's so small from the transfer of information from, AWS, it's not like a transfer.
Right, that doesn't matter. But I like to put it in Git just because of the version control. Or you could have the Git repo cloned on the box, and then you can just push it, you commit it. So I'm saving this file, but then I also need to save my lookup file, right? Because those are my two things that are going to let me actually do some machine learning. So I have another lookup file here, lookup.csv, right? So that's our data processing. Next up is we're going to do some machine learning. So let's say I came in, I've done with this for today, I saved my files to S3, I shut off my instance, I launch a new instance now, and then I'll open up a new Jupyter notebook, and we're going to go through that. So I'm just going to, go ahead and download this so I can give that out to everybody later. And then I'm going to terminate this notebook because I need to free up my memory. Like, this notebook is eating up like 55 gigs right now. So let me go ahead and close this.
Can you force those objects to remove them from memory? Because you're not using them at all.
Yeah. You could, but then you'd have to go through and see which all of the big objects you were using, and like you would say like df equals none is the way you would clear it from memory in Python. But I just close the notebook because that way it cleans up everything.
Because
So,
it seems like the one object that was very big was the sparse one. So
Yes.
if you remove it, so you're gonna have a lot of memory.
yeah, so and that was only an intermediate thing. Because like we needed to have all those zeros in the pandas data frame, and then once we converted it to the matrix, we can clear the other one. But I have a new notebook for the machine learning, so we'll just do that. So next up is the scikit-learn. So in this particular notebook, what we're going to do is we're going to grab our data again. The one that we just saved as S3, we'll pretend it's a different day. And we're going to do that. We're going to do it. All right. So let's download that data. So AWS S3 CPs. So I'm going to just save those both to my current place, 2014 parb.lookup. So the sparse matrix I created and the lookup file, we'll download those. So those are quick, right? They're small files, just a few megs. So let me just go ahead and, I should have copied my imports, but now I got to type all this. We have to set a random state because I'm going to be doing a random forest, just so always best practice to have a random state. And always best practice to set it to the meaning of the world. So 2015. Let me just copy this. Actually, that might work. Yeah. So our labels are going to be in our lookup file, right? Because those are the two strings. And then our features are now from our matrix. So we got to do sp.load_npz. And sparse. So these two guys will take a second. Load npz. So take a look. This is the same exact data we just created, so make sure everything's all good. Those are our labels. And our features is the sparse matrix. We can take a peek at, let's say, the first row or the first column. I don't remember which one's indexed first, but it's a bunch of zeros. Right. So in memory, it actually doesn't materialize these zeros, but then once it shows you to you and you give a dense array back, it gives you the zeros. So what we really came here for is the machine learning. So first of all, always good practice if you're doing any sort of machine learning problem is to create a train test split first. So what we're going to do here is I'm not going to use the test set, but we're going to do a train test split. And then we're going to do essentially a grid search cross-validation on the training set to determine how many trees we need in the random forest. That's our hypothetical scenario right now. So scikit-learn has a train test split, and I can never remember which thing comes in the train test split. So if we look up scikit train test split, because it gives you back 4 things. So you say, give it my x, my y, the test size, random state. Then it gives you x train, x test. I can never remember the order of these, so I'm just going to steal this. And I'm going to use lowercase because I don't like uppercase. So my x in this case is just my features, right, which is my matrix. But my y is just the provider type column. I'm not using MPI in my y. So I have to go to labels, provider type, right? And then we'll set my random state to the variable that we created before. There. So I'm going to do a 2/3, 1/3 train test split. Pretty standard stuff, right? So xtrain.shape, make sure everything's good. So that's going to be, your training is going to be 2/3 of our original data set, right? It was about 500,000. Now we've got like 300,000. All right. Now we're ready to do some models. This case, I'm going to use a random forest classifier from scikit-learn. And so, and I mentioned this before in the last, before the break, is random forest is really nice to use a CPU optimized instance because in scikit-learn you can actually because it's just an ensemble, a bunch of trees, you can distribute that across all your CPUs. So if we were doing a logistic regression, if we were doing an SVM or a decision tree, I wouldn't need all these CPUs because all of the processing would just be within one CPU. I would just need the memory. But because I'm doing a random forest, I can actually utilize all these CPUs. So inside of the random forest, from the API, like if we look up random forest, one of the options here is obviously n estimators, which is the number of trees. But then another option is n jobs, which is essentially the parallelization. Like you would set that essentially to how many cores you want it to use. But you can also just tell Python to just give it all your cores. So that's what I'm going to do now. So that multiprocessing module tells you how many CPUs are on your machine. So now you can just take this code and put it anywhere. So I'm going to say my RF and n estimators, just because I don't want to sit here all day. We're just going to set it to 5 for now. N jobs equals the CPU count. And then our random state, of course, is our random state that we created before. Cool. So that's our random forest. Now we can just fit. So fit, train, y train. Let me do 20 estimators just so we can make sure we take advantage of all our CPUs. So, actually, before I run this too, I'm going to use this magic command, which if you do %% time, if you haven't seen this on your Jupyter notebooks, it'll tell you how long the cell took to run. So now we can see our CPUs are actually starting to warm up and do things.
Could you see what the path is to? Like I see that you use the copy command, you always start off with S3, colon, // so that if you could do like the exclamation, Unix command for the, to get the current directory to your path.
Yep.
And then see that it was like an EC2 instance as opposed to an S3, or I don't know what the path is to this machine that you're on.
Well, so so the S3 has all the same paths. On your machine, the local file system would just be the local file system like you would have on any other server. So if you did like an LS like this, that's your local machine, whatever your home directory is right now.
And if you did like where you are currently, you're in that directory.
Yeah. So but then if I did AWS S3 LS, I would still have to put my bucket. Now this is actually doing an LS on my bucket, but they're two distinct file systems. They don't relate.
Equivalent to AWS EC2.
No, because that is your EC2 that you're on is your current machine. So an LS would show you what's on it right now.
LS is not a local machine, it's your remote machine.
That's true. It's my remote machine because my local machine. Okay, fine. That's true. If I opened up this terminal and did an LS, that's my local machine. It's my remote machine. That's right. That's right.
EC2 machine, right?
Yeah, the EC2 machine. The LS is the.
You don't have a path to it that you can't, like, if you're going to SSH to it, you don't have a path.
Well, that's the public DNS name. So like if you wanted to SCP a file to it, you could with the DNS name.
But you can also, on your EC2 machine, you can also mount a drive that corresponds to your S3, no?
Yes. So you can actually mount drives that are backed by S3 if you wanted to.
Yeah, so I just
Yeah.
don't know exactly what you would put there to mount that path to that drive.
Yeah, I'm not sure how that works either. I know you can do it. I've never done it myself. So, all right. So that's our just single fit. So you saw our CPUs lit up for a second. That ran for 30 seconds to do 20 trees. But now, let's look at the results first. So we'll import some metrics. Since this is a multi-class, we can't do necessarily like a ROC. I mean, we could do a ROC of like one versus all for each thing, but I don't feel like doing that right now. So we're just going to do accuracy, even though it's not always the best thing. So we're going to take our train model, right, predict from the X of the train, and then we'll get the accuracy score. %. So out of the 10 classes, 70%. It's not bad, right? So if we want to see our confusion matrix, so this is just a handy tip. Scikit-learn has a confusion matrix function, but it's really ugly. So I like doing the pandas crosstab, which will actually do it much better. And it's way easier to read. Because the scikit-learn confusion matrix won't give you your strings. It'll just be like 1, 2, 3, 4, 5. So we can actually see our confusion matrix for real now. So we can see some anesthesiologists are being confused with internal medicine. You would expect that internal medicine, family practice are going to be mixed up with a lot of different specialties because they do a lot of different things. But the accuracy of the model is outside of the scope of this. Okay, so the next thing we're going to do, and I guess for time, what we'll do is we'll finish off the machine learning stuff right here, and then we'll take a break, and then we'll do the RStudio stuff after the next break. And then the heavy experimentation part, I can just briefly point you to the right direction if you want to read more, but this stuff is more important anyway. So now what I want to do is I want to do a grid search. So I did this random forest with 20 estimators, but the assumption of random forest, right, is more trees, it gets better, but it's how many trees do I really need? So scikit-learn does have a grid search functionality, right? You can just give it a grid and say, I want to try 10, 20, 30, 40, 50, and it'll run all of those. But especially because we're on an EC2 instance and because we might be running on a spot instance, I'm going to do it a little bit manually. So what I'm going to do is I'm going to try a number of trees, but then every time I train one model, I'm going to save the results to S3. So that way at each step in the training, I'll be able to watch it. Because maybe the random forest with 200 trees takes 30 minutes to train. I don't want to sit here and wait for it. And especially if you're doing a grid search with like 30 items, and then it's not done, and then Amazon kills your instance, you just wasted all of that time and all that money. So at least we're checkpointing and we're seeing where we're going. So that's what we're going to do now. The one thing is to do that, actually, and I don't want to peek ahead. To do that, we need to save files to S3. So we could do the whole thing that we've been doing is saving to the remote path, and then copying from there to S3 with the bash command. But what I'm going to do is show you the Python API for S3, where you can just write the object directly to S3. So it's called Bodo. I have no idea why it's called Bodo, but if you import Bodo 3, that's actually, this Bodo 3 package gives you all of Amazon services. So it's actually just a Python port of the bash API. So there's an AWS CLI, and I'll show you later how to install that. Bodo 3 is an exact mirror to that. So if you just look up Bodo 3, you can see the whole API. You can launch instances. All the stuff that we did through the UI today to launch machines, you could do that through the Python code. And that's actually how I do my heavy experimentation. Rather than having to click around all the time, I just have a script that launches my instances. So the way to get to S3 is you do bodo3.resource S3. So now you have a little handler to give you stuff in S3. So I can say S3 dot, there's a bunch of stuff. So I can say S3 dot bucket. Actually, I don't fully remember what this API is, but anyway, you could look up like Bodo 3 list your S3 stuff, and you can list all the objects. But what I care about right now is basically what I'm going to do is I'm going to train a model. I'm going to get my results into a pandas data frame, and I'm going to save that pandas data frame onto S3 at each iteration of my model training. So for that, I'm just going to create this method, and you're going to have to trust me that it works because I can't explain it fully. But so this is actually straight from my repo that I have if you wanted to grab this method. But essentially what you have to do is you create a string buffer with the IO package in Python, and you save your pandas data frame into that string buffer. So rather than to an actual materialized file, you save it into the buffer, and then you write that buffer directly to S3. So you're actually never going to disk. So actually what I did in my experiments is I never actually attached any storage to my machines. I would only use the RAM, and then I would go straight from the RAM to S3. Then I didn't have to deal with if Spot deleted my instances or dealing with the volumes and everything. But that, you have to be really careful and really know what you're doing with that, because it's nice just to have the disk in case you lose it. But so we create this string buffer, and we do the toCSV, but instead of a file name, we give it the buffer. And then we just set index to whatever we say, but index we're going to default to false for now. And the reason I'm writing this in a function is going to have to use it a bunch of times in a for loop. So, and then this is the Bodo 3 API. It says s3.object bucket key, and then it's going to say put. So it creates, essentially what it does is it creates a new object according to this path that you give it. So S3 : / bucket name / key. And then it's going to put my string buffer. So it's going to say the body equals buff.get value. And I can't take credit for this. You could just Google write CSV to S3 or write pandas data frame to S3, and you can find this. So now I have a method. So let's just test it, right? So I'm going to make a test data frame. And we'll just say column is 1, 2, 3. So here's my dinky little data frame just for testing. So let me test my function. So I'm going to say to CSV S3 and test df and test CSV. So let me just be explicit. My bucket is going to be my private bucket, so not the one accessible to the world. And then my key is just going to be test.csv. So I run that. It never actually went to the hard drive on this machine. It went straight to S3. So now, if I do an AWS S3 ls with this path, we can see some of my other stuff that I'm doing, but that's my test CSV file that I just wrote just now, UTC time, right? So it worked, allegedly. So if I want to prove it, I'll prove it to you. Test.csv, and then I can say, put that here, and then, oops, CP, right? So if I do CP, and then I can just do head, test CSV. And that's the CSV that I just wrote. So that's just a prerequisite before we get to the cool experimentation part. So this last piece, I think I already have the code written for it. And then we can just watch it run. But I can walk through it real fast. So I'm not using scikit's default grid search. Let me do it with just a small number of trees first. So I'm using this cross-validate function, which basically says, give it a classifier. You can give it the X and Y. You give it the metrics that you want to do. And then you tell it how many folds inside of the cross-validation. So actually, if you were doing single-threaded models like logistic regression or anything else, the cross-validate method has an n jobs parameter. So like if you had a grid search and it was single-threaded things, you can actually set this to -1, and it would run your whole grid in parallel. But because I'm doing random forest, it's already running in parallel, so I can't parallelize both because my CPUs are taken. So in this case, it's going to be 1. But if you had any other models, you could set that to -1.
What happens if you have, like, just on a regular machine, you only have so many CPUs, and those equates to your number of jobs that you can do? So what happens if you assign 10 number of jobs and your CPU only have 4?
They would just wait. They would just be blocked until the other ones. So
It won't blow up. Right?
it wouldn't. Don't quote me on that, but I think the processes would just block until they're ready to go. But it doesn't make sense because now it's not optimized. You would want it to be however many CPUs you have. So basically what I'm doing here is I'm going through the number of trees that I want. I have a classifier with that number of trees, right? I run this cross-validate, which will do, in this case, a 3-fold cross-validation. It gives me back these accuracy and balanced accuracy metrics. I append it to my current data frame with the concat method, and then here is I'm actually saving it to S3 every single time. So I'm building up this data frame. Every single time I add a new entry, I'm just going to save it because I want to be able to see the progress as it goes on. Because if these numbers go, this model might train for hours, right? So then I can get it to keep going. So we'll run it with just 2 and 3 just so I can show you. But then normally what I do if I'm doing something in a Jupyter notebook, if I had a long-running thing and then I wanted to go to sleep, I'd turn this on because I'm really confident that my code's not going to break, and then I would set the shutdown, so it would shut down later. So if there's an exception in the notebook, the shutdown would trigger, or if it actually completed successfully, the shutdown would trigger. So we can see here now that some model stuff is happening. It's going to do the 2 and 3 trees, and then we'll save the CSV, and then I'll kick it off with the full job, and then we'll take a break and come back, and then it'll be ready to go. It's complaining. Oh, that's just some warnings about deprecation.
Question?
Yeah.
Because you say the question, you say that if there is more threads than available who handles parallel processing on such examples? It's Jupyter or it's scikit-learn?
That does the that actually does the multi-threading?
Yeah.
Yeah, so scikit-learn handles it for you, but I think it uses the multi-processing package from Python. I'm not 100% sure though.
Okay.
Yeah. Yeah, Python has like 2 or 3 multi-threading packages, and Python's not the best for multi-threading, but it like multi-processing I found is the best one. There's also thread and some other ones, but this one it's nice because scikit-learn does it for you, so it's easy to do. Okay, so that's ready. So now I just want to show you what the data frame looks like from this cross-validate method. So if we look at our data frame, what did I call it? Out? Yeah. So now it just created this. So what I did is I do the cross-validate. I add an entry to the dictionary for my number of trees, so I actually know what I ran. And then I create a data frame from that thing, concatenate it to the one that I've been building up. So now there's this right here. We have our number of trees, and then these are all the metrics that the Spark cross-validate runs. It'll give you the test bound, all the metrics that you asked for. So if I go into my actual local computer, this is my laptop, I can copy that because I have the permissions and users set up on my computer. I'll show you how to do that later. But then I can, where did I save this? I can grab this file and put it, let's say, in my downloads folder. Oh, I spelled my own name wrong. There. Boom. Okay, so now that's in my results folder. Put it in my downloads. And results. Right there. Same file. So what we're going to do after the break is I'm going to kick off this job to run with all of these numbers of trees. It's going to take a while to run. And then we're going to build a Shiny app with R that's going to connect to that file in S3. It's going to download that file, and it's going to create a dashboard so we can monitor our progress of the job. So it would continually ping. Well, I'm not going to build that part, but you could refresh the page, and then the page will be refreshed now with the results of your experiment. So if you think about you're running a bunch of experiments, a bunch of grid searches, it's going to take a long time. You can write all of your results to S3 and then build this little dashboard to monitor it. So
can you build a dashboard that's totally independent of R, right? So if you want to build...
Oh, yeah, you can build anything. So there's a file on S3 now, and anything can get to S3. So you have a file on S3, you can build it however you want to, but I just chose to build it with R and Shiny, but you could even use Tableau or something like that, or just download it yourself if you don't really care too much to have a dashboard. But all right, I'm going to kick this off. It's just before 4 o'clock, so we'll come back at 4:10, 4:15. I'll see how many people are back in the room, but we'll take a quick break again, and then we'll come back for the R part.